Data is the lifeblood of the modern energy sector. Energy leaders now treat data as a strategic production asset. In upstream operations alone, digitalization yields savings of about $3.30 per barrel. But extracting those savings requires navigating a structural barrier, the deep historical divide between the computing environments that run the business and the engineering systems that extract the resource. This is the arbitrary duality between information technology, or IT, and operational technology, or OT. Constructing a functional digital oil field requires understanding and ultimately dismantling this historical wall. Information technology manages commercial computing. This is the domain of enterprise resource planning, human resources, and business data. IT systems prioritize fluid environments, relying on frequent updates, constant security patches, and data center performance. Operational technology operates under a different set of rules. OT directly monitors and controls physical infrastructure, like the valves, pumps, and processing units on a rig. The primary metrics here are 24/7 uptime and fail-safe reliability. These systems are highly stable, often remaining unchanged for decades. These priorities create an inherent conflict. IT requires constant updates for security, while OT views external changes to a working system as a direct threat. Historically, these domains lived in separate worlds. IT occupied climate-controlled rooms housing the massive, isolated scale of legacy mainframes, while OT was governed by a hands-on, physically demanding environment where technicians manually adjusted analog wall panels in industrial control rooms. Keeping these departments in silos gave birth to a widespread industry problem known as the data monster. Because accountability is split under diffused governance, a chief information officer handling commercial systems, and a chief operating officer managing the physical assets, the resulting data environments are fragmented and inconsistent. The result is severe inefficiency. In legacy environments, engineers can spend up to 40% of their time searching for and cleaning bad data before they can perform any actual analysis. For decades, the backbone of operational technology has been SCADA, supervisory control and data acquisition systems. To guarantee security, legacy SCADA networks were air-gapped, meaning they were physically severed from the outside internet. These closed loops relied on dumb iron, equipment capable only of basic self-reporting telemetry that pinged a central server with simple measurements. That isolated architecture is dissolving, driven primarily by the rapidly falling cost of data storage, analytics, and connectivity. Computer chips have become so small and power-efficient that the industry can apply cheap math, making it economically feasible to install sensors on almost every physical asset. This networked hardware forms the Industrial Internet of Things, or IIoT, effectively replacing legacy SCADA setups. The defining feature of IIoT is edge computing. Computational power moves from a distant server directly to the remote device. Using local AI, the sensor filters raw data streams, transmitting only high-value packets, like anomaly alerts, to the broader network. Edge computing upgrades passive dumb iron into autonomous smart iron. These machines can self-diagnose and request their own servicing. By processing data at the source, edge-enabled IIoT optimizes network bandwidth while delivering the instantaneous, real-time insights that air-gapped SCADA systems lacked. To harvest this data, operators must bypass proprietary supplier systems, often called walled gardens, that block different pieces of equipment from communicating with each other. This requires a new digital architecture built on 3 pillars. The first is open, standards-based systems. Equipment from different vendors must act as plug-and-play technology, similar to modern military hardware. The second pillar connects the physical sprawl of legacy operations through wireless blanketing. Utilizing inexpensive wireless networks allow companies to connect massive multi-acre sites without the expense of digging trenches and laying miles of new cable. The third pillar is cloud integration. This involves pooling information into a data lake, a single cloud repository that stores both the commercial IT records and the physical OT measurements in their original formats. To make this repository usable, teams apply descriptive metadata to the files, ensuring that the merged datasets remain searchable. Together, open standards, wireless networking, and centralized cloud storage bypass departmental silos to establish a unified foundation for enterprise-wide analytics. Executing this architecture requires replacing diffuse management with a joint team governance model. This model brings together 4 distinct roles. IT specialists, for instance, exposes a severe friction point, managing cybersecurity in connected operations. When legacy systems move from air-gapped obscurity to internet-connected networks, the digital attack surface expands. Malicious bots can sweep the internet and discover newly connected machinery within minutes. The danger lies in older, brownfield OT hardware. These devices lack the processing memory to run modern encryption, and many use hard-coded passwords that cannot be changed. The consequences are physical. A compromised sensor can trick a control system into improperly opening high-pressure valves, resulting in catastrophic damage or environmental harm. Organizations cannot reap the efficiencies of digitalization unless they treat cyber attacks on physical infrastructure as high-probability, high-impact events that require board-level strategy. Despite these security hurdles, the operational payoffs of IT and OT convergence justify the risks. Applying integrated data analytics to a network of smart iron can reduce unplanned equipment failure by up to 90%. The ultimate expression of this efficiency is the gas factory model. By utilizing centralized cloud platforms to coordinate dozens of specialized service companies, operators transform the chaotic process of well delivery into a virtual assembly line. In remote regions of Australia, Convergence allows drone flights to autonomously inspect over 150 wells a day, feeding high-resolution imagery directly into the next day's optimized maintenance roster. This diagram of the carbon cycle maps atmospheric CO2 exchange. Tracking carbon for trading requires taking physical telemetry data, the domain of OT, and merging it with the commercial tax ledgers managed by IT. These integrated capabilities allow legacy providers to transition toward business models that are information-heavy and asset-light. In the converged digital oil field, value is derived from the intelligent interpretation of data rather than the mere ownership of heavy machinery.